A quantum computer in Palo Alto solved a problem in minutes. The same problem, run on Frontier, the most powerful classical supercomputer on the planet, housed inside Oak Ridge National Laboratory, would take nearly 1 million years to solve with the same accuracy. And it would burn through more electricity than the entire human race consumes in 12 months. Read that again. Not faster, not more efficient. A different category of machine entirely, solving a real problem, not a party trick, while sipping power roughly equal to 2 ordinary houses running their air conditioning. Somewhere right now, $650 billion is being poured into data centers built on the old assumption that this kind of gap would never actually arrive. It just did. To understand why this result matters, and why the title of this video isn't quite the whole story, you first need to understand exactly what happened inside a research paper published in the journal Science on March 12th of 2025, because the details here are stranger and more specific than the headlines that followed it. A company called D-Wave Quantum, working with an international team of scientists, took their advantage to prototype a quantum annular packing more than 5,000 qubits, and pointed it at a genuinely difficult physics problem, simulating the quantum dynamics of something called programmable spin glasses. Think of spin glasses as disordered magnetic materials, the kind of substance where the tiny magnetic orientation of individual atoms doesn't settle into a neat, predictable pattern, but instead tangles into a chaotic, frustrated mess that's brutally difficult to model mathematically. Understanding exactly how these materials behave matters enormously in the real world, because magnetic materials sit at the heart of medical imaging machines, electronics, superconductors, sensors, and motors. The invisible infrastructure running through nearly every piece of modern technology you've touched today. D-Wave's quantum computer worked through the simulation in a matter of minutes. The same calculation, run on Frontier, the supercomputer widely considered the most powerful classical machine currently operating anywhere on Earth, would have needed something in the neighborhood of 1 million years to reach the same level of accuracy. And according to the research team, it would have consumed more electricity than the entire world uses in an entire calendar year just to get there. This is not chaos. This is strategy, or at least it's the closest thing to genuine, verifiable proof that quantum computing has finally crossed a threshold researchers have been chasing for decades. The line separating an impressive but ultimately useless laboratory stunt from something that actually solves a problem people care about. And this distinction matters enormously because it separates this specific result from earlier, more controversial claims of quantum supremacy that came before it. Back in 2019, when Google first claimed its Sycamore processor had achieved quantum supremacy, critics quickly pointed out that the specific task involved, something called random circuit sampling, was deliberately engineered to be difficult for classical computers and functionally useless for anything else. It proved a point about raw computational power, but it didn't cure a disease, design a better battery, or solve a problem anyone outside a physics department actually needed solved. D. Wave's chief executive officer, Alan Baratz, drew this exact distinction with striking directness when the research was announced. This was not just solving a problem that can't be solved classically, he said. This was solving an important, useful real-world problem. Read that again, because it's the entire thesis of why this result generated so much more serious attention than prior quantum computing headlines. This wasn't a magic trick built to impress physicists. This was a quantum computer doing something a hospital's MRI research team, a battery manufacturer, or an electronics company might genuinely need done, and doing it in minutes instead of a length of time longer than human civilization has existed. The scientific community's response to this claim wasn't uniform celebration, and an honest telling of this story has to include that friction, because it's exactly the kind of scrutiny that makes a genuine breakthrough more credible once it survives the process, rather than less credible for having faced it in the first place. Independent researchers immediately began probing the specific comparison D-Wave had made, asking the same hard question that had chipped away at parts of Google's 2019 claim years earlier. Was the classical comparison actually fair? Had the research team used the best possible classical algorithms and the most optimized classical hardware available? Or was there still room for clever computer scientists to close some of that million-year gap through smarter software rather than fundamentally new hardware? This is precisely the kind of adversarial, skeptical process serious science is supposed to survive, and it's worth being upfront about rather than pretending this result arrived wrapped in unanimous agreement. Dr. Hidetoshi Nishimori, a physics professor at the Tokyo Institute of Technology with no direct financial stake in D-Wave's success, offered his own independent assessment once the dust had settled somewhat. He called the paper a significant milestone in demonstrating the real-world applicability of large-scale quantum computation, a carefully worded endorsement from someone whose entire career depends on getting these judgments right. Here's where this story genuinely earns the dramatic framing sitting in this video's title, at least in one specific technical sense worth understanding clearly. The energy numbers involved aren't just impressive, they're almost absurd when you actually sit with them side by side. According to the published research, D-Wave's entire quantum calculation ran on approximately 12 kilowatts of power, an amount of electricity roughly equivalent to what 2 ordinary American homes consume running their normal daily appliances. Now place that number next to the classical alternative, a calculation that would have required more electrical energy than the entire population of Earth uses across an entire year, running on a supercomputer housed inside one of the most sophisticated, most heavily funded computing facilities on the planet. This is the exact comparison that should make anyone paying attention to the current AI infrastructure boom sit up and take notice, because it strikes directly at the single most expensive, most physically constrained resource driving the entire data center industry right now. Not computing chips, not real estate, electricity. Every AI data center currently under construction anywhere in the world is fundamentally a bet that the industry can secure enough electrical power fast enough to keep an ever-expanding fleet of energy-hungry classical chips running around the clock. D-Wave's result suggests, at least for this specific narrow category of problem, that an entirely different approach might accomplish the same underlying goal using a small fraction of that power, running on hardware that looks nothing like the endless rows of GPU racks currently filling data centers from Virginia to Singapore. D-Wave's own chief scientist, Mohammed Amin, framed the potential downstream applications of this breakthrough in genuinely sweeping terms. "There's no shortage of potential applications," he explained, describing a future where entirely new materials could be simulated and effectively invented on a quantum computer before anyone ever needs to physically synthesize them in a laboratory and test whether they actually work. Think about what that could mean in practical terms. Pharmaceutical researchers testing new drug compounds without months of expensive physical trial and error. Battery engineers designing next-generation materials for electric vehicles without years of iterative lab work. Even something as mundane as your cell phone or a pacemaker keeping someone's heart beating steadily, both mentioned explicitly by D-Wave as potential beneficiaries of materials that were simulated into existence on a quantum processor before a single physical sample was ever manufactured. This is where the genuine, deserved excitement in this story lives. Not in some vague, sweeping claim about obsolete data centers, but in the specific, concrete possibility that an entire category of expensive, time-consuming, energy-intensive scientific work might be compressed from years down to minutes, and from massive power consumption down to something you could plug into an ordinary household outlet twice over. But here's the honest, necessary turn the story has to take before it earns your trust for everything that follows. Because the title promising every data center built today has suddenly become obsolete simply isn't supported by the actual evidence, and pretending otherwise would be doing you a disservice. The financial reality of the data center industry right now points in almost the exact opposite direction of obsolescence. Global capital spending on data center infrastructure is projected to exceed $1.7 trillion by the year 2030, according to current industry analysis, and that number isn't declining in anticipation of quantum computing, making it unnecessary. It's accelerating, driven overwhelmingly by the explosive growth of artificial intelligence, edge computing, and high-performance computing workloads that show no signs of slowing down. AI computing demand specifically is expected to more than triple between 2025 and 2030. Read that again, and sit with the contradiction it creates against this video's own title. If a quantum breakthrough had genuinely rendered today's data centers obsolete, you would expect the smartest, most well-informed capital in the world, the venture funds, the hyperscale technology companies, the institutional investors pouring money into this exact sector to be pulling back, redirecting their billions toward quantum infrastructure instead. That isn't what's happening. $650 billion was committed to AI data centers in 2026 alone, an amount that dwarfs the entire quantum computing industry's total investment many times over. One particularly clear-eyed piece of industry analysis put this exact tension into words that deserve to be quoted directly, because they cut through the hype far better than any paraphrase could. Data centers are not becoming obsolete, the assessment states bluntly. They are, by nearly every measure, in the middle of their largest expansion in history. This is the honest concession this story demands before it can responsibly continue, and it's worth understanding precisely why both things can be true simultaneously, why D-Wave's breakthrough can be genuinely, scientifically remarkable, and why data centers can, at the exact same moment, be expanding faster than at any point in human history. The distinction that resolves this apparent contradiction is actually simple once you see it clearly. Individual data center facilities absolutely do become obsolete over time, the way any piece of physical infrastructure eventually ages out and gets replaced by something newer. But the underlying concept of centralized computing infrastructure itself isn't shrinking. It's growing more essential with every passing year. even as quantum computing matures alongside it, layered on top of the classical infrastructure rather than tearing it down and replacing it wholesale. This is precisely the framing that data center industry insiders themselves have started using to describe what's actually happening. And it's a far more interesting, more accurate story than the simple obsolescence narrative this video's title implies. Andy Power, president and CEO of Digital Realty, one of the largest data center real estate companies in the world, described the industry's evolution using a memorable metaphor during a conversation about the company's 20 years of growth. Data center demand, he explained, behaves like a layer cake, with each new wave of technological advancement adding an entirely new layer on top of everything that came before it, rather than scraping away and replacing the layers underneath. Cloud computing was a layer. Artificial intelligence became the next, dramatically larger layer sitting on top of cloud infrastructure. And now, according to industry trade publications tracking exactly this trend, quantum computing is emerging as the newest layer in that same cake, described explicitly as the latest demand layer, moving out of research laboratories and into genuine commercial deployment. Notice the language here carefully. A demand layer, not a demand replacement. Something being added to the existing structure, not something tearing it down. Understanding exactly why quantum computing is more likely to become a new layer than a total replacement requires grappling honestly with the physical, practical engineering challenges still standing between today's laboratory quantum systems and any kind of wholesale infrastructure takeover. A detailed report from S&P Global specifically examining this exact question, whether quantum computing might disrupt existing data center environments, offers a genuinely sober, carefully hedged assessment. While the report acknowledges that quantum computing has the potential to transform the world of computing, it's equally direct about the reality on the ground right now. Integrating quantum computing into existing data center environments, the report states, is rife with complexity. Quantum computers today remain, in the report's own blunt phrasing, bulky, finicky, and non-standard. A genuinely significant obstacle as this technology tries to move beyond isolated research labs and into the kind of standardized, reliable, commercial environments that modern data centers depend on to function at scale. Think about what that means practically. D-Wave's remarkable Advantage 2 system, the very machine that produced this million years versus minutes result, isn't something you can simply swap into an existing server rack the way you'd upgrade a graphics card. Quantum architectures require uniquely customized environments, distinct enough from a classical infrastructure that the report specifically predicts quantum systems capable of playing nicely alongside existing classical compute infrastructure will hold a genuine commercial advantage over systems that demand a completely separate, isolated environment all their own. This engineering reality connects directly to something worth understanding about the broader timeline the entire quantum computing industry is currently working against, because it tempers the breathless urgency this video's title implies with a far more measured, far more credible picture of when quantum computing might actually reshape data center economics at meaningful scale. According to Ellie Brown, a quantum computing and cloud economics analyst at S&P Global Market Intelligence, most industry roadmaps currently place the genuine implementation of commercially transformative quantum systems somewhere in the 2028 to 2032 timeframe. Not next year, not even necessarily by 2027, a 5 to 7 year runway from where the industry currently stands. UBS analysts, in a detailed 103-page report published in January of 2026, offered a similarly measured but still genuinely exciting timeline, stating that the industry is close to completing a quantum computer that could cost tens of millions of dollars to build, but that would be capable of solving a specific problem in 200 seconds that would take a conventional supercomputer dramatically longer to match. Madeleine Jenkins, the UBS analyst who led that report, made a statement worth repeating in full because it captures the genuine, carefully bounded confidence serious financial analysts are now willing to express about this technology. I would not be able to say this with this much clarity last year, she said, but this year I can state to claim that by 2029 you will have machines that will have commercial value, meaning that they will be doing calculations that classical machines cannot do. Read that again. Not this year, not next year. By 2029, according to one of the more credible, carefully researched analyses currently circulating through the financial industry. Jenkins also directly addressed the exact energy question this video opened with, and her framing deserves to be heard in her own words rather than paraphrased into something less precise. When it comes to quantum computing's impact on data center energy demand specifically, she stated that quantum computing would require a fraction of what a data center would use to solve equivalent problems. But she was equally clear about where the truly transformative advantage actually lives. The big thing is time, she explained, describing how a problem that might currently occupy a data center's resources for thousands upon thousands of hours could theoretically be compressed dramatically once mature quantum systems come fully online. This is the honest, carefully bounded version of the exciting claim buried inside this video's title. Not obsolescence, compression, not replacement, acceleration, layered directly on top of the classical infrastructure that will continue running the overwhelming majority of the world's computing workloads for the foreseeable future, doing the specific narrow category of problems quantum computers happen to be extraordinarily good at, while classical data centers continue handling everything else: the web searches, the video streaming, the ordinary business software, the vast majority of artificial intelligence training and inference that has nothing to do with simulating exotic magnetic materials, the encryption protecting everything stored inside those racks in the first place. Security researchers and policy analysts have spent the past several years increasingly focused on a specific, well-documented threat pattern known as harvest now, decrypt later, a strategy where adversaries, whether hostile nation-states or sophisticated criminal organizations, quietly copy and store enormous quantities of encrypted data today, patiently waiting for the day quantum computing hardware finally matures enough to crack that encryption wide open retroactively. Industry analysis throughout 2026 has increasingly framed this concern using a specific term, quantum sovereignty, describing assured access to quantum computing capabilities and genuinely secure communications as a strategic national priority. Some analysts now compare directly to nuclear deterrence and its long-term importance. There's even a specific name circulating for the moment this threat becomes fully realized, something researchers call Y2Q, the point at which the encryption standards protecting nearly all of today's digital infrastructure officially become computationally obsolete against a sufficiently powerful quantum adversary. Read that carefully, because it's a far more precise, far more defensible version of the claim sitting in this video's title. It's not the physical servers, the cooling systems, or the electrical infrastructure inside today's data centers becoming obsolete. It's the mathematical locks currently protecting everything stored inside them, a distinction that matters enormously for anyone trying to understand exactly where the real, credible urgency in this story actually lives. Think about what this means for the $650 billion currently being poured into new data center construction this year alone, because it reframes the entire risk conversation in a way the simple obsolescence narrative completely misses. The physical buildings, the cooling systems, the electrical substations, the actual racks of computing hardware, none of that becomes worthless the moment a sufficiently powerful quantum computer finally arrives. What becomes urgently, immediately vulnerable is any sensitive data currently protected using encryption standards that a mature quantum computer could eventually break, which is precisely why security researchers have spent recent years pushing organizations to adopt something called crypto-agility, the ability to rapidly swap out vulnerable encryption methods for newer, quantum-resistant alternatives before that Y2Q moment actually arrives, rather than waiting until the threat becomes an active, ongoing crisis. This is where the genuine urgency in this story lives, not in some dramatic image of today's data centers sitting empty and abandoned, but in a quieter, more technical race, currently unfolding largely outside public view, between organizations racing to upgrade their encryption before quantum computers mature enough to threaten it, and adversaries who may already be quietly stockpiling encrypted data today, patiently waiting for that exact moment to arrive. So where does all of this actually leave the specific dramatic claim sitting in this video's own title? The honest, carefully researched answer requires holding two genuinely true things in your mind at the exact same time, without collapsing either one into the other for the sake of a cleaner, more viral-sounding story. D-Wave's March 2025 breakthrough is real, peer-reviewed, published in one of the most rigorous scientific journals on Earth, and genuinely represents a meaningful, application-relevant milestone in the decades-long effort to prove quantum computers can do something classical computers fundamentally cannot, on a problem that actually matters to real industries rather than existing purely as an abstract benchmark. The energy numbers involved, 12 kilowatts against more electricity than the entire world consumes in a year, are genuinely, legitimately staggering, and they point toward a future where certain narrow categories of scientific and industrial computation could eventually be compressed dramatically, both in time and in the sheer physical resources required to complete them. But the sweeping claim that this breakthrough has already made every data center built today obsolete simply isn't supported by where the actual evidence currently points. Data center capital spending is accelerating, not slowing. Quantum computing hardware remains, by the industry's own honest assessment, bulky, finicky, and difficult to integrate into existing infrastructure. The most credible expert timelines place genuinely commercial value quantum computing somewhere between 2028 and 2032, years away, rather than an event that has already fully arrived. And the real, Immediate obsolescence risk currently facing data centers has far less to do with quantum computers making classical hardware unnecessary and far more to do with quantum computers eventually making today's encryption standards dangerously insecure, a threat that demands urgent preparation now, but that hasn't yet arrived at the crisis point. Some of the more dramatic headlines circulating online would have you believe what's actually unfolding here is something more interesting than simple obsolescence, and arguably more useful to understand if you're trying to make sense of where this entire industry is genuinely headed. Quantum computing isn't coming to replace the data center. It's coming to move in alongside it, becoming, exactly as industry insiders now describe it, the newest layer in an increasingly tall, increasingly complex cake of computing infrastructure, sitting on top of decades of accumulated classical hardware investment rather than tearing that foundation out from underneath it. The trillion-dollar data center boom, currently reshaping skylines from Virginia to Singapore, isn't a bet that quantum computing will never arrive. It's a bet that classical computing, however it eventually gets supplemented by quantum systems handling narrow, specialized workloads, will remain the dominant, indispensable foundation of the digital world for the foreseeable future, with quantum computers eventually earning their place as powerful, specialized tools working alongside that foundation rather than replacing it outright. If you want to understand exactly what happens once quantum computing crosses from these narrow, application-specific breakthroughs into the kind of broad, general-purpose commercial value UBS analysts are now confidently predicting for 2029. And what that transition actually looks like for the data centers currently being built right now, that's precisely the story we'll be tracking closely as it unfolds. So make sure you're subscribed before that transition arrives. Before you go, I want to know what you honestly think about everything you've just heard. Does D-Wave's breakthrough feel like the beginning of a genuine transformation in how the world computes, even if it arrives more gradually and more collaboratively with existing infrastructure than a dramatic headline might suggest? Or do you think the sheer scale of money currently flowing into classical data centers proves the smart money still isn't worried about obsolescence anytime soon? Leave your honest answer down in the comments below. And as always, I rate every single one.